Okay, I would like to present a work done with my PhD student, Alexis Burdeau, in Paris, and also for the second part of the talk with the collaboration of Christine Combs and Jeffrey Olafsen of the Department of Physics in Baylor University in Texas. The outline of my talk is divided in three. I would like to start by the motivation of this work and also by a brief review of experimental setup. Secondly, I would like to present our molecular dynamics or DAM simulation. First, we have to validate the model we use and also the result we have found. And the third part is devoted to the velocity statistic of a single particle with a new series of experiments performed by Jeffrey and Christine. The basic idea of work is based on a common sentence that the fact you have energy dissipation in collision, the granular particles obviously need an external source of energy, and even in a steady state, the velocity distribution are generally non-Gaussian and are dependent on the heating mechanism. Several kinetic theory have been developed for homogeneous systems, and we can do a lot of calculation to the condition that the system is homogeneous, and in some case where the heating is idealized. The two main examples, I just wrote the basic equation of motion equation for a particle and the corresponding Boltzmann equation, in which this is the bin, okay. And here you have a term due to the heating mechanism. The two classic heating mechanisms are the deterministic forces given by the Gaussian thermostat, and the force is given with xi is positive coefficient. This gives this term for the Boltzmann equation, and the stochastic thermostat in which you have this term for the Boltzmann equation. And with that, you can perform a perturbative solution of the distribution, the velocity distribution. That means you are close, but not with Maxwell-Boltzmann equation like in equilibrium. Thus, we have the goal to find system which minimize the non-Gaussian velocity statistic, and also because generally it's difficult also to understand what are the microscopic mechanism at the origin of this characteristic. We start by the experimental setup. Probably 10 years ago, Jeffrey with Urbach started an interesting system in which we have a two-dimensional monolayer. You have a cylinder in which you just put one monolayer of steel particles, and you gently accelerate the bottom plate, and the control parameter is dimensionless acceleration given by the amplitude of the vibrating plate times the omega square divided by the gravity. And in the first paper, they consider a very small acceleration, and they observe very interesting characteristics like clustering, order, and also collapse. But this is not the regime in which we are interested. And they also, in a second paper, increase the value of gamma, and I just take the result about the flatness, which is a very important parameter for the non-Gaussianity, which is the ratio between the force moment over the square of the second moment of the distribution. And as you can see, when you increase the dimensionless acceleration, you progressively decrease the deviation to Gaussian, knowing that for a pure Gaussian, you have a value of 3. And also for an exponential, you have the value of 6. Note that you have, in these experiments, two kinds of beads of different size, and the result is the same if the lead is sufficiently above the vibrating plate. That means that the particles remains only at the bottom, and they no collide with the leads. It's true that its gamma is become larger. Sometimes particles are able to leave the first layer, but if you add a lead, the flatness is larger than 3. Some years later, Prévost also used the same system with the modification that instead of the smooth circular plate, he considered a rough hexagonal, but hexagonal it's not very important, but he considered a roof plate. And in this case, for the same value of acceleration, gamma equal 1.5, the distributions become more Gaussian, the deviation is less, and you can see here several curves of the velocity distribution for different coverage, and for a small value of the coverage, the deviation from Gaussian is small. I also would like to mention the work of Pedro Weiss and Mark that Pedro explained very well, but about the glassy dynamics of crystallization and so on. And I would like now to focus on the experiment of Baxter and Olafson, in which instead of monolayers, they use a bilayer, and the first layer is consists of a dense layer of dimers, of steel dimers. The dimers are connected by a small bar, and on the second layer, the top layer, is composed of less dense particles, generally plastic particles, Delrin particles. And you can see here a photograph of the experimental setup. This is a part of the cylinder, and you can see at the bottom the steel dimer and above the plastic particles. And they have obtained, I'm sorry, because all curves are collapsed on the same graph. It was published in Nature, probably a small room. But as you can see, I just indicate in red, all curves of corresponding to the top layers are very close to the Gaussian given by the full curves, whereas the first layer deviates largely. I also forget to mention that this corresponds to the horizontal velocity. We do not consider the vertical velocity even for the top of the second layer. There are deviations from Gaussian. We have tried to reproduce at least these phenomena, but it was difficult to consider interaction for steel dimers, and we have replaced the steel dimers only by art sphere, sword sphere, because we are using a spring dashpot model who can forces for overlap and also dissipative viscous force, very classical. And just few details on the model. The time step is 10 minus 5 seconds, the light particles correspond exactly to the experimental mass, as well as for the heavy particles. The simulation were performed to the dimensionless acceleration, and for different value of the frequency, we change the amplitude accordingly. And except because in the experiment you have several thousands of dimers, we just take here a smaller system with periodic boundary condition, and we check that we change the size of the system, the result are not changed, and we vary the coefficient of restitution in a range sufficiently large. And we have only one parameter in order to match the granular temperature of the top layer. And the first qualitative result is that we have obtained that the granular temperature decreases with increasing frequency and with increasing coverage of the top layer. But I have also now a small movie. And the tailwind particles are in blue, and the still particles are in red. And you have obviously an idea of, I'm sorry, of the result, which is
just click below where the go down to the bottom of the screen and click on your slide. It's there.
Become slide show.
No, well, move your cursor all the way down where there's
Yeah.
a slide behind the. Go down a little further. A little further. Now click there. Oh, down. Oh.
no. I'm sorry.
All the way down.
Seems to.
Where your slide is behind the PowerPoint.
No.
There.
Okay. Sorry. The results are the following. For the different value of the coefficient of restitution, all velocity distribution of the top layer are very, very close to the Gaussian. It's close to 3 to 1%. For relatively small coverage, because we only have 20% of the top layer covered. We have also studied the flatness versus the coverage, and we increase the coverage of the top layer. It's true that if you are for very dense top layer, you deviate from the Gaussian, but for quite dense system, you are close to the Gaussian. We have also varied the mass ratio. Initially in the experiment, the mass of the system of the first layer are higher than for the top layer. And as you can see, we have a variation quite difficult to interpret, because if you consider two coverage of the top layer, the variation of the flatness is increased when the top layer is, the coverage of the top layer is equal to 20%, and decrease when the top layer is equal to 40%. The experimental value corresponds to this case of the ratio of the mass. But it remains very close. We have also considered the structure, and for two different size of the particle of the top layer, as you can see, at long distance, you have a small oscillation of the structure if you have particles of the same size. This oscillation disappears if the particles of the top layer are larger than the particles of the first layer. To go further, we try to analyze the trajectory of the particles, and we have a typical trajectory of the particles. In red correspond to the collision with the first layer. In blue, the collision between particles of the top layer. And we have here an efficient mechanism which randomizes the direction and also the velocity of the particles, and probably leads to the Gaussian statistic. We have also simulate the case very close to the Prévost experiment, because we have glued the particles of the first layer. We keep the rough surface, and all the parameters are unchanged, and we have observed that the flatness is not deeply modified, but significantly less than 3 for the same coverage. In summary, the surface roughness due to the first layer randomizes the direction and of the post-collisional velocity of the light particles, and when the EV particles are allowed to move, the magnitude of the light particle is also modified almost randomly during collision. And we are now sure with the simulation that this phenomena is robust if you change the large mass ratio and various degrees of inelasticity. The story could be over, but Jeffrey started a new series experiment. He would like to consider only a single particle. And in order to have correct data, he has to reduce the size of the cell and only put one single daring particle. This is, again, a photograph of the experiment, but you have all the cells now. These correspond to the different shell on which you follow the trajectory of the single particle. And they measure the flatness of the both layers. You have here the second layer formed by the single daring particle, and for different value of the shell. As you can see, except close to the boundary, the flatness is quite independent of the distance. And you have here the flatness of the first layer. It's a big difference, second and first layer.
So what are the colors?
The color correspond to the different color of the shell of the trajectory. But we tried to reproduce this experiment like previous experiment, but we failed a long time. And in fact, there are some difficulty due to the fact that in this experiment, the coverage of the first layer is smaller than in the large cylinder. It's easy to calculate that for 23 diamonds, the coverage of the first layer is equal to 0.73. And by using spheres instead of dimers in our simulation, we always have the tracer particles which falls into the monolayer. And in this case, it's not possible to restart the simulation, and the statistic is obviously completely wrong. We try to modify the model because we have to incorporate the effect of the dimers bar. Because we have dimers, as you can see, the two spheres are able to move away a little bit from each other. And how to try? We just use a very mean field model in which we just add the virtual floor for the single top particle, and if you have a hole in which the top particle can fall. You consider that in this case you have a collision with a virtual fall, which represent in parts the connector between dimers. It was a very simple model, and we try to compare to the experimental results. This is the velocity distribution of the first layer, in which you have a very huge deviation to the Gaussian. As you can see, you have in full curve the simulation result. You have the Gaussian, and you have all collected data from experiment. It's very close to the experiment. It's a very simple model, for to reproduce the experimental data. And for the top layer, for the single particles, we are rather close. There's more deviation in experimental data than in simulation. In conclusion, I have to add the fact, if you are using, instead of fixed rough surface for heating, you are using a simple first layer in which the particles are able to move. You have to use a very dense first layer, because if you add defect, you modify deeply the velocity distribution of the top layer. And I also drawn here a simple graph on which you have the parameter on which you can play the dimensionless acceleration. It's better to use dimensionless acceleration between 2 and 3, mass ratio less than 1, a size ratio also not too large, and also to limited coverage for the top layer. Thank you for your attention.
Thank you. Does anybody have any comments or questions apropos of Pascal's presentation? Charlie.
I'm confused. What's the goal of this project?
The goal is to find or to build an experimental setup, and also to try to understand by molecular simulation a system on which you are able to have a heating mechanism in which the particles have Gaussian velocity distribution, or very close to the Gaussian. Because we know that the steady state depends of the heating, and if we are close to the Gaussian, it's easier. Yeah.
There's a parameter that people come up with that measures the number of collisions with the bath compared to the number of collisions between the particles in the system. Do you have, in the experiments they can't answer that question, but from your simulations, how many more times are you colliding with the bath than with each other? The
ratio progressively, the number of collision between particles of the top layer increase when you increase the coverage. But the main point is to keep a reasonable acceleration of order 2. If you had a lead, but in your experiment you have a lead, generally you deviate from Gaussian, but it's probably
you tend to deviate from Gaussian whenever you're colliding with your neighbors more than you're colliding with the bath. And the more you collide with your neighbors compared to the bath, the farther the deviation.
Yeah, it's important to have a rough surface for changing the direction of the velocity, and.
But if you collide with the bath 10 times for every time you collide with a neighbor, you're just measuring the bath. You're not making another fluid.
Yeah, it seems to be important to have more collision with the bath.
Yes. Okay.
Yeah. But we try also we try also to have a lead like in our experiment. It's better you have a quasi-gaussian US even for higher acceleration. But in this case, you need to have a rough lead, and it's not very easy for experiment to have too opaque from above and at the bottom.
That is clear.
Okay, I have two observations. The first one is just the same as that has been done. If you have two time scales which are relevant for the process, the collisional time between particles and the collision bandwidth is one. Okay. And the second is that past work has shown that in general there is some relationship between partial correlations of particles and velocity distribution. So I think it could be interesting in your system to investigate also the spatial correlation, if it changes, how change with different situations which you can observe different velocities.
That's more a comment.
Okay.
Thank you. That's a good comment. Thank you very much. Mike, you want to ask a question?
Well, I'm sorry this will seem like a really stupid question.
We love stupid questions.
But
Well,
I am a stupid speaker.
It's always important to ask stupid questions, I think. It's probably just a cultural language thing, but what actually is a dimer?
Dimer,
What?
two particles connected by a bar, a small bar.
Right.
But
In the experiment, sometimes you have glued dimers. You do two spheres, give a dimer.
Right.
Dimer is.
so a polymer is many parts of a dimer.
Yeah.
Ah, I see. Okay.
But they are elastic, aren't they?
Elastic. It's not elastic. They are able to move away for
They are linked to
until